We already know of the trig functions sin, cos, and tan. So now we're going to introduce three more trig functions, which are sec, cosec, and cot. And these are reciprocals. Remember, reciprocal is 1 over something. These are reciprocals of trig functions that we already know, where sec x is equal to 1 over cos x, cosec x is equal to 1 over sin x, and cot x is equal to 1 over tan x. Now, as tan x, as we know from first year, is equal to sin x over cos x. We can also write cot x as cos x over sin x, like this. Now, the full names of these are secant, cosecant, and cotangent, respectively, although this isn't that important. And a way that someone taught me, a good way to remember these, is it's the third letter in each of the trig functions that it is the reciprocal of. So you can see it's c here, and then it's cos here, it's s here, and it's sin here, and it's t here, and it's tan here, if you need help remembering it. Now, another thing is, as we can't divide by 0, in the definition for sec x here, this only works when cos x is not equal to 0, because if cos x is equal to 0, then therefore we'd be dividing by 0, and we just can't do this. This is the same for cosec of x. Sin x cannot be equal to 0, as we'd be dividing by 0 here. And for the definition for cot of x, tan of x can't be equal to 0 either, and also sin of x can't be equal to 0, although tan x and sin x are equal to 0 for the same x values, so we don't really need to write this sin x part. You can't put these trig functions directly into your calculator. There's no sec function, for example, built into your calculator, but finding their values is incredibly easy. So for example, let's say we need to find sec of 60 degrees. This is just equal to 1 over cos of 60 degrees using the formula here, which is equal to 1 over, and then if you put cos of 60 degrees into your calculator, you get out the value of a half, and then this is just equal to 1 over a half. Now, if you don't know, if you have 1 over a fraction like this will just flip this fraction here, so this will become 2 over 1, so therefore this will become 2, like this. For cosec of 2 pi over 3, this is going to be equal to 1 over sin of 2 pi over 3, like this. And if you put this into a calculator, sin of 2 pi over 3, as we're working in radians, make sure that your calculator is in the radians mode. I talked about this in the radians basics video of last chapter, so go back to that if you need to. This will be equal to 1 over, and then sin of 2 pi over 3 is equal to root 3 over 2, like this. So therefore this fraction will be flipped here to 2 over root 3, which if you then rationalise the denominator, it will come out as 2 root 3 over 3, like this. Cosec of 2 pi over 3 is equal to 2 root 3 over 3. And then finally, cot of 5 pi over 4. There's obviously two ways you can do this. The first way you can do it is do tan of 5 pi over 4 over 1, like this, which if you put tan of 5 pi over 4 into a calculator, it's equal to 1, so it's just 1 over 1, which is equal to 1. Or the other way you can do it is using the cos x over sin x, so this is going to be equal to cos of 5 pi over 4 over sin of 5 pi over 4. If you put these into your calculator, they both come out as minus root 2 over 2, which is obviously just equal to 1. So cot of 5 pi over 4 is equal to 1. You need to be aware of what the graphs of these functions look like. So let's start with sec of x is equal to 1 over cos x, and let's do it in degrees first. So let's start with what we already know, which is the cos graph, and let's consider some values to understand what this graph will look like. So for cos of x is equal to 1, which is here, the sec x will be equal to 1 over 1, which will still be equal to 1. So this point here will remain unchanged. For cos of x is equal to 0.5, which let's say is about here, this will be equal to 1 over 0.5, which is equal to 2. So this point here is going to be about here. For cos of x is equal to 0.25, which we'll say is about here, this will become 1 over 0.25, which is equal to 4. So let's say this is about here for example. And then for cos of x is equal to 0.1, this would be equal to 1 over 0.1, which is equal to 10. So this point will be way up here. And what happens, you can see, is the smaller that cos x gets, the infinitely bigger that sec x is going to get for that point. So the graph is going to look like this. So it's going to start from 1 and then it's going to come up like this forever, and then it's going to do the exact same on this side here like this, where this will keep going up and up and up forever to infinity into the thousands and millions like this. But where cos of x is equal to 0 like here, this is going to be 1 divided by 0, and remember, you can't divide by 0, it doesn't work. So this here is going to be an asymptote, where this graph of sec of x never meets this line here, and there is no value for sec of x where x is equal to 90 degrees like this. And basically this shape here is repeated for all the other parts. So it works the same for negative, so it starts from -1, then it comes down really quickly like this, and then the same for this side here, and then it's the same for this here. This starts at 1 and then it comes up really quickly here. This comes down really quickly at -1, and then it's the same here, and then this comes up really quickly like this. And there's going to be asymptote to all of the points where cos of x is equal to 0. So this is equal to 0, so there's going to be an asymptote here. There's going to be an asymptote here, and there's going to be an asymptote here as well. And then this is the graph of y is equal to sec of x like this. Now the way I sort of remember this graph is, firstly, for whatever version that we're doing, so we're doing cos of x here, I always draw the original graph because the shape's quite weird and I kind of struggle to remember it and where exactly it goes, so I always draw the original graph. And for all of the graphs in this video, they are all sort of a reflection in the line y is equal to 1 like this, and for the negative parts it's y is equal to -1. You can see that they're all kind of sort of a reflection in this line, where this comes up to here and then this comes down to here and stuff like that. It's sort of a reflection. It's not exactly a reflection because obviously this crosses 90, whereas this just keeps going on forever and ever. But you can sort of see the relationship of how it's reflected like this. And what you find is this is the case for all of the graphs in this video, for the sec, the cosec, and the cot graph. So the specification specifically talks about the domain and range of these functions. So I made a functions video in first year about what domains and ranges are, but basically the domain of a function is the set of x inputs that you can put into it. So for sec of x, you can basically put any x value into the function, which we write as x, and then we kind of put this trident symbol here, and then we put this r here, where this r means all real numbers. However, this is except for when cos of x is equal to 0, as we said before, because then we'd be dividing by 0. So therefore x cannot be equal to when cos of x is equal to 0. So we can see this is for plus and minus 90 degrees, and then plus or minus 270 degrees, because cos of x is equal to 0. And this will keep going on forever, because remember, the cos graph goes on forever like this. And then the range of a function is the set of possible y outputs. And this is when y is bigger than or equal to 1, or when y is less than or equal to -1. You can see that all of the values for sec of x either lie above 1 or they lie below -1. This region here between 1 and -1, there is no values for sec of x. It can also be equal to 1 and -1 here and here, for example. And then this, of course, could also be in radians, where everything is the same except for the values on the x-axis, obviously, and the values in the domain, where now it can't be equal to plus or minus pi over 2 or plus or minus 3 pi over 2. The range is the exact same, as it's the same function, just with different units. Now let's do the graph of cosec x, which is equal to 1 over sin x. So again, I've started with the normal sin graph here, and it's the same looking graph as before. We've sorted the mirror in this kind of y is equal to 1 line like this, where it starts at y is equal to 1, and then it comes up like this here quickly, and then up like this again here, and then here it comes down quickly like this, and it's the same here. Here it comes down quickly as well, like that. And then it's the same here, where it comes up quickly, like this here. And the asymptotes are going to be when sin x is equal to 0. So remember, there won't be values for this because you can't divide it by 0. So this is here, here. There is also one on the y-axis line like this, and there is also going to be one at minus 360 and also at 360. So this is the graph of y is equal to cosec of x. The domain is similar to before, where x can be any real value except when sin of x is equal to 0. So therefore this is when x is equal to 0 here, when x is equal to plus or minus 180 degrees, or when x is equal to plus or minus 360 degrees, and then this will keep going like this. And then the range is the same as before. Y has to be bigger than or equal to 1, or y has to be less than or equal to minus 1. There is still no graph in this section here between 1 and minus 1. And again, this could be in radians as well, with the domain now being all real x values except when x is equal to 0, plus or minus pi, plus or minus 2 pi, so on. So now let's do the graph of cot x, which is equal to 1 over tan x. So let's do the same thing as before. Let's start with the graph of y is equal to tan x. Now this one's obviously going to look a bit different because the tan graph looks different to the sin and the cos graphs, but it's still got the same idea that it's sort of a reflection, not exactly, but it's still sort of a reflection in the lines y is equal to 1 and y is equal to minus 1. So let's start with this bit here. So this here is going to be reflected to here, like this, but rather than going up and up forever and ever, instead it's going to cross at the x-axis here at 0. So it's going to be like this here instead, and then it's going to meet at this point here, and then this part of the line is going to be reflected like this, but instead of crossing the x-axis at 0 like this, it's going to be like this line, where it just keeps going up forever and ever and ever like this. Maybe a better way of saying it is it's actually kind of reflected like this, but it still has the same features of the previous graphs, where it's still kind of reflected in these lines here. So it's the same for this here. This here is going to be reflected in this line, so it sort of becomes like this here, but instead it's now crosses at the x-axis, and this is going to be reflected here, but it's now going to come up and up and up forever like this here. So this here is now going to be like this here, and then this is going to come up like this, and then this is going to be like this here, and then it's going to continue like this, and then this is going to be like this, just quickly like that. Then this is going to come up like this to here, and then this is going to come down like this to here, and then this is going to come up to here like this here. And the asymptotes are going to be when tan of x is equal to 0, because again you can't do that. So there's going to be an asymptote here at minus 180, there's going to be an asymptote here at the y-axis, There's going to be an asymptote of 180. There's also going to be an asymptote of 360 here, and at minus 360. So this is the graph of y is equal to cot x. So the domain again is going to be when x is all real values except when tan x is equal to 0. So this is at 0 itself. This is at plus and minus 180 degrees. And also at plus or minus 360 degrees. And then of course there's going to be more values after this as well. Now the range is actually different from the previous two. The range is actually also all real values. It's both when it's above 1 like this, it's both when it's below minus 1 like this, but you can see that there are values between 1 and minus 1 this time as well in these kind of areas here. So therefore all values of y can be outputted. And again, this could also be in radians, where the domain would instead be all real values of x except when x is equal to 0, plus or minus pi, or plus or minus 2 pi, and so on. Finally, they could ask you to transform these graphs. Now, we've talked all about transformations before in Chapter 4, Year 1, and we also talked about it in the Trigonometric Graph Transformations video in Year 1 as well. So go back to those videos if you need to. But here's an example where we need to sketch the graph of y is equal to 2 sec of x in the interval 0 to 2 pi. Now, I've talked about this before. The best way to do graph transformations, in my opinion, is to first sketch the untranslated graph. So this would be y is equal to sec x, and then base the transformations around this. So first sketch this, and whenever we're doing a sec, cosec or cot sketch, in my opinion, because these are quite complicated graphs to remember, I would always draw the original graph. So in this case sec x is equal to cos x under 1. I would always sketch the cos x graph and then base my sec sketch around this. It's just because this is quite a complicated graph to remember from memory. So instead use a sketch of y is equal to cos of x in order to help you know where each point goes. So for y is equal to sec of x, remember it starts from 1 and then it comes up like this here, and it starts from here and then it comes down quickly like this, and then like this, and then this comes up really quickly like this here. And this is the graph of y is equal to sec of x. So again, whenever you need to draw y is equal to sec, cosec or cot x, I would draw the original graph and base your new graph around these, because these can be quite hard to know where the specific points start from. Because this is quite a small axis, I've got rid of the cos graph to avoid it getting a bit too messy, but in your exam it's perfectly fine to leave your working in the cos graph. So now we need to do the actual transformation, which is y is equal to 2 sec of x. So this is an outside the function stretch, so it's going to stretch everything by 2 in the y direction. So this here, which is at 1, is now going to be at 2 here, so now it's going to be here and it's going to come up like this, and then this here, which was at 1, is now going to be at 2, so it's going to come up like this here, and then this here, which was at -1, is now going to be at -2, so now this is going to be here, so this is going to come down like this here. So this is the graph of y is equal to 2 sec of x. Now this is our very final graph that they're asking us to actually draw, so we should draw in the asymptotes as well. There's an asymptote here at pi over 2 and an asymptote here at 3 pi over 2, and then this is the final answer. So here's another example. So as I said before, I think the best thing to do is to first sketch the untranslated graph, which is going to be y is equal to cot x, and as cot x is equal to 1 over tan x, I think it's good to first draw the tan graph to base your drawing of the cot graph around this. So I've quickly drawn a tan graph like this, and then the cot graph is going to start from 90 like this and then come up to here, and it's going to come up like this here, and then it's going to come down to here, and then keep going down like this. Remember, it's sort of reflected in the line of this is 1 of y is equal to 1 and y is equal to minus 1 here. And then on this side, it's going to come down like this here, and it's going to keep coming down like this, and then it's going to come up like this here, and then up like this. And then this is the graph of y is equal to cot x. So now we're going to do the actual transformation. So this is y is equal to cot of 2x. So we have this 2 here. So this is an inside the function stretch. So this, remember, is going to have the opposite effect of what you're expecting. So it's actually going to squeeze everything by 2 in the x direction. So this here is at 90. So this here is now going to be at 45 degrees like this root here. So this is going to start like this, and then it's going to come up here, and then this here is now going to come down, and it's going to come down to 90 instead of coming at 180. And remember that because it goes on forever, that we're going to get the exact same shape here, but it's going to keep going. So we're going to get this shape here like this, and then we're going to keep going down like this here, where we just haven't included this in this particular interval here, where this is at 135 degrees like this, and then this minus 90 is now going to be at minus 45 degrees, where this is going to come down like this here, and then this here is now going to come up here to minus 90 degrees, and then there's going to be one here as well that's going to come down like this here, and then this is going to come up like this, where this is going to be at minus 135 degrees. So this is the graph of y is equal to cot of 2x. So remember that we need to sketch in the asymptotes. So there's going to be an asymptote here between here and here. So there's going to be an asymptote here. There's an asymptote at minus 90, and there's also going to be an asymptote at minus 180 and at 180 here. So here's one final example where we need to sketch a graph of y is equal to 2 minus cosec x. Now I'm actually going to rewrite this as y is equal to minus cosec x plus 2 like this. I think this is a bit clearer that we've got this minus and then this plus 2 like this, so it's easier to see what transformations we need to do. So firstly, we should sketch the graph of y is equal to cosec x, the untranslated graph, and remember that cosec x is equal to sin x under 1. So I've quickly drawn a sin graph here, so therefore cosec of x is going to start from here and it's going to come up like this quickly, and then it's going to come up like this as well, and then it's going to start from down here and come down like this, and then it's going to come down like this here, and then this is the graph of y is equal to cosec x. So now let's do the actual transformations, and we have two transformations. We have this minus 1 here, and we also have this plus 2. So it's a multiple transformations question. Now we talked about how to do this in year 1. So go back to that video if you need a reminder. But basically, we need to do each transformation one at a time, and the order in which we do it is kind of the order in which it affects the function. You can sort of think about this in like bid maths or bod maths. Remember back in GCSE, if you think about it like that. But basically, this minus is going to have its effect first because it's minus cosec x, and then it's going to be the plus 2 like this. So first we're going to do the minus, and then we're going to do the plus 2. So firstly, let's do the transformation y is equal to minus cosec x like this. So this is an outside the function mirroring. So this is going to, if you remember, mirror everything in the x-axis like this. So this now is going to come down here. It's going to start from minus 1 instead of 1, and it's going to be like this here. Then on this side, it's going to be like this, and then this here is going to be mirrored in the x-axis. Minus 1 is going to become 1, so this is now going to be like this here, and then like this here. So this is the graph of y is equal to minus cosec x, where it's mirrored in the x-axis. So I've just extended the axis quick, and now we need to do this transformation. So now we need to sketch a graph of y is equal to minus cosec x plus 2. So this is an outside the function translation, so this is going to shift everything up by 2 in the y-axis direction. So this, which was at 1, is now going to be at 3, which we'll say is about here. So this was at 1 and now it's going to be at 3. So this here is now going to be like this here and here. And then this, which was at minus 1, is now going to be minus 1 plus 2, which is equal to 1. So this now is going to be here. So this is going to start from here and it's going to come down again like this here. And it's going to come down like this here. And then this is the graph of y is equal to minus cosec x plus 2, and we need to sketch the asymptotes in for our final graph. So there is an asymptote here at pi, there is an asymptote at 2 pi, and there is also going to be an asymptote at 0. This can be kind of hard to see sometimes because we've done the transformations already, but there's going to be an asymptote between this and these this line here.